All right, let's dive into something pretty fascinating. We're going to explore the challenge of teaching logic, the very bedrock of how computers think, how to handle uncertainty.
So let's start with what sounds like a simple question, but one with a really complex answer. How do you actually program a machine, a thing that thinks in absolute ones and zeros, to understand the idea of maybe, or I'm not sure? This one question, it really pushes classical logic to its absolute limits. And look, this isn't just some dusty academic puzzle. It's totally fundamental if we want to build machines that can reason more like we do, machines that can handle a world that, let's be honest, is almost never just black and white. Okay, let's get into it. So, first things first, we've got to go back to the beginning, to the system of logic we're all familiar with, and really understand why it just doesn't quite cut it for this task. And that right there, that perfectly highlights the core of the problem, doesn't it? Our actual world is messy. It's full of uncertainty, of ignorance, of doubt. A simple true or false system just can't begin to capture all that richness. So logicians had to invent some brand new tools. So our first stop on this journey is to see how logicians first tried to tackle the most basic kind of not knowing, just plain old ignorance. Now, what's so interesting here is the distinction being made. It turns out there are levels to not knowing. On the one hand, you might just not know the answer to a question. Simple enough. But on the other hand, you might not even understand what the question means. That is a much, much deeper kind of ignorance. So to formally capture this idea of severe ignorance, logicians had to get creative. One of the big breakthroughs was something called three-valued logic. It basically shatters the true-false binary by adding a third option, unknown. This lets a system represent a state where something isn't true or false for an agent simply because they don't have the context to even make a judgment. But ignorance is kind of a passive state. What about the active state of being unsure, of weighing different possibilities? Well, that brings us to the logic of doubt. So this is the really crucial point. Logic itself had to evolve. If you want to model a mind that can actually doubt something, you have to create new categories for what truth can even be. It's not just about missing information anymore. It's about actively juggling multiple and sometimes even conflicting bits of information. This table shows the evolution so clearly. You start with classical logic, simple, clean, true or false. Then clean logic comes along and adds unknown to deal with that ignorance we were talking about. But then Bellnap-Dunn logic takes it a step further and adds a fourth value, both. This is for those weird situations where an agent has conflicting evidence. Some of it says a statement is true, and some says it's false at the same time. Okay, so having these categories is a huge step. But can we get even more precise? Can we actually put a number on our uncertainty? Let's see how logicians tried to do just that. And this is a massive leap forward. Instead of just saying a statement is unknown, now we can say something like, I'm about 70% sure it's true. This gives us a much more nuanced and frankly realistic way to represent what's going on in an agent's mind. This introduces a really fantastic idea called the Lockean thesis. It basically suggests that what we call belief in our everyday lives isn't actually 100% certainty. Nope. It's just having a credence or a degree of belief that's high enough for us to act on, which, when you think about it, lines up so much better with how we actually think and make decisions in a world that's anything but certain. Okay, we've covered a lot of ground here. 3 values, 4 values, probabilities. So how does all this stuff actually fit together? Well, there's a perfect analogy that helps make it all click. Let's use this simple idea of a jigsaw puzzle to visualize these pretty abstract concepts. Just think of figuring out the truth as trying to find the one right piece for an empty spot on the board. This is our severe ignorance. The agent is just missing the fundamental info needed to even think about the problem. The puzzle piece isn't just unknown, you don't even know it exists. You literally can't even start to solve this part of the puzzle. Now, here the agent actually has information, a bunch of possible pieces, but they just can't commit to a single one. This is exactly where that probabilistic logic we talked about comes in handy. It helps the agent weigh the options and give each piece a degree of belief that it's the right fit. And this perfectly captures that both value from Bellnap-Dunn logic. The agent is dealing with conflicting information. You have 2 different pieces of evidence that both seem right, but they just can't exist together. The system has to have a way to represent that paradox without breaking. At the end of the day, this isn't just a philosophical exercise. It is the actual blueprint for building smarter, more adaptable AI. An AI that can function in our complex, messy, and uncertain world has to be able to say, I don't know, or I'm not sure, or my data seems to be conflicting. It's all about creating machines that can reason with nuance. And that's the big, provocative thought we want to leave you with. As we get better and better at modeling these very human states of uncertainty, we open up a whole new can of worms, new questions about the future of intelligence itself, both artificial and our own. And that's a question that logicians, AI developers, and really all of us are going to be grappling with for years to come.